So the last time we spoke on Friday, we were pretty much just getting into muscle metabolism, and we were starting the conversation about the source of energy for muscle contraction. So essentially, where does muscle get its ATP from? And so we talked about these three sources of ATP. One we said was pretty temporary, just to get the muscles started, to initiate muscle contraction, and to just kind of have it on tap, we describe that as, and just in reserve for initiating that contraction, getting it going, while the other two more sustainable processes kind of got started, got warmed up. And so that temporary process was the creatine phosphate system, which is where we can make ATP, have it on tap for when muscle wants to start contracting. And then the other two processes, we said oxidative phosphorylation. We talked about this when we looked at cellular respiration. So we should be familiar with this process. This happens in the mitochondria across the inner mitochondrial membrane. This, we said, produces more ATP. It's more of an efficient source of ATP, but it requires oxygen. We're going to talk about how that plays into the fiber typing because of this source of ATP production. And then the third source of ATP, and the second more sustainable source of ATP, was anaerobic glycolysis. So again, we know what glycolysis is, right? Those enzymatic reactions that break down glucose to make ATP, not as much ATP as oxidative phosphorylation can, but this doesn't require oxygen, so it can happen anaerobically. And then there is a cost for that anaerobic ATP production, which I'll talk about in a bit, okay? So that's kind of where we got to. We described the actual process of how creatine works, right? It's kind of shuttling that phosphate back and forth. It can be on creatine, or we can drive this reaction to the right, where we can take that phosphate off of creatine, put it onto ADP and make ATP. And this happens via the enzyme creatine kinase. And so when we use up ATP, we drive the reaction to the right to make more of that ATP. And if we've got enough ATP on hand, we can start driving the reaction to the left in order to not make too much ATP, if that makes sense, right? Back towards creatine and the phosphate on creatine. And by the way, this is where we get that creatine supplementation that I'm sure you may have heard of, with bodybuilders and athletes. It's thought that this supplementing creatine could somehow improve athletic performance, as it would, increase the amount of energy production for muscles. That's not quite clear, it's not conclusive if that happens, but we do know that it can increase short-term energy performance. But whether or not that is sustained is still up in the air because of the negative feedback system with creatine production. So if the body sees too much creatine, it's actually going to shut down creatine production where it's normally made, which is in the liver, the kidneys, and I think the pancreas. So the pancreas, liver, and kidneys can make this creatine and then store it in muscle. But if we have exogenous creatine, which comes in via that supplementation, it's thought that the negative feedback could shut that down. And so the jury's still out on whether or not that actually does enhance, athletic performance. So let's now move on to speak about different types of exercises, different types of intensity exercise and physical activity, and how metabolism can change with those different intensities. So we'll start by looking at moderate or light intensity exercise and how muscles get their energy during that type of activity. So it's mainly sustained from oxidative phosphorylation. And the reason for this, when we think about the different types of intensity, you want to be thinking about how feasible it is to maintain ventilation. So if I can maintain my ventilation, then I can get enough oxygen in, and that can sustain or maintain oxygen going to muscles, and that can drive that oxidative phosphorylation, which we know relies on oxygen. If I can't maintain my ventilation, the muscles are going to have to seek another route to make ATP anaerobically, which doesn't require oxygen. So just bear that in mind as we talk about these different types of intensity exercises. So if I'm doing a light, moderate intensity activity, and again, here we want to think about light jogging, walking, maybe house cleaning, or walking around the shopping mall, grocery store. So light or moderate intensity exercise where you can actually maintain your rate of breathing. Initially, the muscles are going to tap into their stores. So remember, glycogen is being stored in liver and muscle. And so muscle has already got some glycogen being stored there, and it can tap into that glycogen via glycogenolysis and break that down to glucose and use that for ATP production initially. And then up to 30 minutes, the muscle is going to actually seek glucose and fatty acid that are being circulated in the blood, and it can use that to sustain its contraction up to about 30 minutes or so. Beyond that period, to sustain, again, light intensity activities like walking, we're going to need to keep ventilation going. And so we can tap into oxidative phosphorylation, which we can sustain because we can maintain our rate of breathing. So in order to keep that oxidative phosphorylation going, oxygen supply must be kept adequate. So we've got to keep our ventilation going. We've got to keep our heart rate, up to sustain that circulation of oxygen in the blood. We've got to keep the contractility of the heart going. And then we've got to be able to dilate vessels to allow that blood to flow to muscles adequately so that that oxygen can be transported to those muscles. Now, while we're increasing our uptake, so during that initial 30-minute window, as we're seeking glucose and fatty acids that's circulating in the blood, we also want to increase, temporarily at least, our GLUT4 transporters in the muscle membrane. So in order to be able to take up that glucose that's circulated in the blood, again, within that 30-minute period, we have to transiently increase the amount of GLUT4 transporters. Remember, glucose needs these transporters in order to move through that cell membrane. And so if you look at our graph here, we're comparing the amount of energy used per the source and time at the bottom. And we can see that initially all muscles are going to start off with this creatine phosphate source for ATP. That's just going to get things warmed up. It doesn't last very long, 1 to 2 minutes, up to I think 5 or so minutes max. And then we're going to start to look to some of these other more sustainable sources. Initially, we can start with glycolysis, again, because we have glycogen lingering around, and we've got fatty acids and glucose, things that we can make into glucose in the bloodstream. And so we're going to tap into that for a little bit, up to 30 minutes. That's this green curve here. And then beyond that, in order to keep oxidative phosphorylation going, to maintain this type of light activity, we're going to keep our ventilation going, keep our heart rate and rhythm, up, and dilate those vessels so that we can get oxygen going to those muscles and sustain this oxidative phosphorylation. When we look at heavier intensity exercise, and here we want to think, not jogging, but sprinting, heavy lifting, strenuous, vigorous physical activity, this is going to rely on anaerobic glycolysis. And again, the main reason here is that we are unable to maintain that rate of ventilation that we could for some of those lighter intensity activities. And the price to pay that I talked about here is the lactate buildup. So when we make ATP anaerobically, and I'm going to go back to this this chart here, this illustration here. When we make ATP anaerobically, remember that because we're not driving oxidative phosphorylation, all of these processes kind of back up and pyruvate starts to build up. And as pyruvate builds up, it actually gets shuttled via lactate dehydrogenase to make lactate. And lactate is an acid. It's sometimes converted to lactic acid. It's an acid. It's going to create that burn that we feel in muscles when we do this type of heavy intensity, strenuous or vigorous activity. And so this is the price to pay of making ATP anaerobically, is that lactate buildup, that burn that we feel in the muscles. Also, the idea that we don't even produce adequate amounts of ATP, and so this cannot be sustained for very long. We only make about 2 net ATP per molecule of glucose, and so that's nowhere near the amount of energy that we can make for lighter intensity activities via oxidative phosphorylation. So both of these methods of energy production have their positive sides, have their advantages, but they also have disadvantages, right? So anaerobic glycolysis makes ATP more quickly, but we have that price to pay with the lactic acid buildup and the idea that it doesn't make as much ATP as oxidative phosphorylation, which makes a lot more ATP, but it requires oxygen, so we have to maintain that rate of ventilation. All right. I'm going to pause here just a little bit, see if you have any questions, and then I'll keep going. So the next thing we're going to get into here is skeletal muscle fibers and fiber typing. And this is probably the most exciting part of muscle for me. This is where most of my research revolves around muscle morphology, fiber typing, changes that we see to muscle based upon muscular dystrophies, based upon, working out, bulking up muscles, or atrophy if we don't use muscles, or disuse atrophy. As well as aging. So how muscle fiber types change just through the normal process of aging. So really exciting part of muscle for me at least. And it's really based upon two aspects of muscle function. So a fiber type is based upon the speed of muscle contraction, fast versus slow, as well as the primary source of ATP, excuse me. So where does that muscle rely on most of its ATP production from? Whether it's oxidative phosphorylation, we're gonna call it an oxidative fiber, or if it's anaerobic glycolysis, we're gonna call it a glycolytic fiber. And so we'll start by talking about the speed of the contraction first. And you can think about this as the first name of the muscle. So muscle has two names. The first name is based upon the speed of its contraction. And we have different types of fibers on that basis. We've got fast twitch fibers and slow twitch fibers. And this really depends on the rate of myosin ATPase activity in the myosin heads. So remember, the myosin heads are what are driving, energizing the whole cross-bridge cycling process. And so that ATP hydrolysis, how fast that can happen is going to be the rate limiting step of muscle contraction. If we can hydrolyze that ATP quickly, then the muscle will then, form those cross-bridge cycles faster, and then the rate of contraction will kind of go faster based upon that. And so we have fast fibers, which have a fast myosin ATPase activity. That means that the myosin head can hydrolyze the ATP more quickly and drive another cross-bridge cycle much more quickly than our slow fibers, which have a slow rate of myosin ATPase activity. And so we can think about it in the time that it will take one myosin head, if it's a fast fiber, to hydrolyze ATP, make that connection with actin, drive another cross-bridge cycling. The time that it'll take one fast fiber to the time that it'll take one slow fiber to make one cross-bridge cycle, a fast fiber can make 3, 4, 5 times that many cross-bridge cycles because it has a faster myosin ATPase activity. And so we can compare the rate of fast and slow fiber contractions. So a fast fiber can contract 2 to 3 times more rapidly than slow fibers. And they also have a rate of relaxation that is faster than slow fibers. So we talked about this a little bit earlier when we spoke about the calcium ATPase and the role of pumping that calcium back into the sarcoplasmic reticulum as a way to clear the sarcoplasm of calcium and as a way to relax the muscle. And if that can happen faster, if the muscle can relax faster because it has a faster calcium ATPase rate, then it can also contract more rapidly. And so a fast fiber not only has a faster myosin ATPase and can form cross-bridge cycles more rapidly, but it's also got a faster calcium ATPase and it can clear the sarcoplasm and relax more rapidly as well. And so slow fibers can contract, much longer in terms of sustaining that contraction when we look at comparing a slow fiber to a fast fiber, the sustaining of that contraction can be up to 10 times longer than it is for faster fibers. All right, so this graph illustrates this idea, and I want to make a disclaimer here that different types of muscles, we talked about this, have different maximum tensions. And so we're seeing here that all 3 of these muscles are drawn at the same peak tension, just as a measure of illustrating the rate at which they can get to that maximum tension. But we want to appreciate that different muscles actually have different maximum or peak tensions that they have. So when we look at these 3 muscles, the extraocular muscles, for example, the gastrocnemius and the soleus, they have different rates of contraction. And so if I stimulate the extraocular muscle, it'll take 7 to 8 seconds to get to its 100% of its maximum tension production. If I stimulate the gastrocnemius muscle, it'll take about 40 seconds to get to 100% of its maximum tension production. The soleus muscle is going to take much longer. And this is how we determine, or how we can appreciate rather, the different weights of those myosin ATPase heads, of the myosin ATPase activity, in looking at the time that it takes a muscle to go from being stimulated to get to its maximum tension production, and how long that can happen, how long it takes that muscle to get there. And so the extraocular muscles are going to be faster, fast twitch fibers. They're going to, contract very quickly, 7 to 8 milliseconds. The gastrocnemius muscle is more of a power muscle. It's used in, fast activities, so things like kicking and, jumping and running. And so it's going to need to be a little bit more responsive and a little bit faster in its contraction than the soleus muscle, which is more of a postural muscle. It's more involved in long-term activities like walking for long periods, standing, maintaining posture for long periods of time. And so we can see that reflected in their rates of contraction here, their speed of contraction.